Hi, everyone. Thank you for joining. Thank you for participating in this special CLIMACT seminar dedicated to research by early career researchers. We invite you to be especially engaging during the question period so they get feedback on their research. Today's seminar will be recorded as usually and will be available on our YouTube channel. As always, only the presentations are put online and not the discussions. As usual, each expert will present for about 20 minutes. It will be followed by a period of question. The seminar will conclude at 1:15 maximum. So without further ado, please let me introduce our first expert, Fatemeh Zakeri. Fatemeh is a geoscience researcher at the University of Lausanne GAIA Laboratory since 2020. Her work primarily involves producing consistent earth science data by analyzing climate data and remote sensing images. She is focused on high-resolution imaging of snow cover and snow water equivalent, essential for understanding environmental changes. Thank you, Fatemeh, for joining us. The floor is yours.
Thank you very much. Thank you, Nicola, for hosting, and thank you, everyone, for attending. I want to share my screen. I also want to use this opportunity and give a shout out to my both supervisor, Grégoire Marieto from UNIL and Emmanuel from UC Berkeley. Without their support, of course, this work even wouldn't come to my mind to do something like this. And for today, I would focus to the subtitle, how we can have high resolution snow forecast. Of course, I am focusing on snow, but the methodology could be also applied to other climate variability and variables. And I will follow on. Here, you can see the outline, general outline. I will start with the motivation, why and how we downscale snow data prediction. And after that, based on that, actually, I will say that why we should focusing on forecasting efforts, and we should do it now. And following that, I will propose the method and the results, and our future perspective would be the for snow for Switzerland would be the finalizing our talk. Here I'm showing before actually starting with why and how. I will start what is downscaling in general. So in downscaling, you try to earn higher resolution data using the coarse resolution data set. You can see on the east that I'm showing Western Swiss Alps that most of you are familiar. The elevation map that can vary from low elevation to high, and this also affects the snow as well as land cover varying through the region. And at the top, at the down, I'm showing the snow water equivalent, the amount of snow that we can get for this region. And you can see for Aero 5, which is 28 kilometer reanalysis data, we just have 4 pixels. And if we go to OSHD service with 1 kilometer data, you can see more detail. And this is really important for water management and other studies. And with downscaling, we try to get this, have higher resolution data set. And this would start with using reanalysis or global climate model that they call GCMs. And they try to do this downscaling. And statistical methods and dynamic methods are those two main methodology for doing so. We'll start with the statistical downscaling. It's very clear from its name that it establishes the statistical relationship between low resolution data and high resolution data. And they forecast based on this pattern, and they are low cost computing and easy to implement. And then we can have ensemble of downscaling. And in the dynamical downscaling, they try to actually do this downscaling using physical models. And based on that physical models, get the higher resolution data. They are high cost computing and time consuming. And but they are better in capturing extreme comparing to a statistical downscaling. That is always, this is the concern, the stationarity concern, that how we can rely on the patterns on the past to forecast for future. But if we could actually have a refined method for this downscaling, trying to be in between, like a statistical and physical model, which would be the focus of our methodology, then we might have better results, and this will be done in the method that we have developed. And why we should do this downscaling, especially for snow. On the right, I'm showing a map of Switzerland. That is, you can see the change, the number of snowfall days in Switzerland comparing to 30 years average before. And you can see that we would have less snowy days in Switzerland. And the temperature in general is twice more than the global average increase in Switzerland. And this will affect the snow cover, especially we would have mostly rain rather than snow in winter, and we would have low, the number of the snowy days would be decreased. And this would have a large impact on hydropower, for example, which is 60% of the energy coming from Switzerland is hydropower. And this would affect this, and also winter sport that is more understandable for people. And I will go to how we will start with our method. Actually, we should select those features that have the most impact on snow when we want to do this downscaling. We do this by actually checking several subset of features and find the best. And after that, we would have two different data sets, one learning data set and the other test data set. For the learning data set, you can see that I'm showing a window of selected features. This window actually, because we are not looking on the exact day, and this is important later in our talk, that we are looking on the past, also history, and then we all know that, for example, a snow here today might come from 2 weeks before or even 1 month before. And by considering this temporal interval, actually we are considering physics, and we are using Aero5 reanalysis for our learning data sets that are more reliable. And for test data set or predicting data sets, we will have those climate variables, but from GCMs, from CMIP6, but we do not have actually a query data set high resolution for the learning data, which is not the case. For the test days, we do not have the high resolution data set that we want to predict, but which is not the case for the learning dates. We already have them. And then we try to find the best candidates based on the matrix that we define. And then using these candidates, the best candidates, we try to estimate the target output. Here I'm showing an animation of the method. You can see that I'm showing the query data set that are already introduced, and the selected feature for our case would be minimum and maximum temperature, precipitation, and surface downwelling short wave radiation. And for the learning days, we all have these features, which comes from Aero5 this time, but for the query days come from GCMs, and also we have high resolution data, and we compute this distance matrix between our query days and other learning days like this, and then we will have several distance matrix, and we try to rank it to find the best candidate. And based on those best candidates, we can actually estimate the output of high resolution. As we talked, a goal for us is SUI prediction daily 1 kilometer. And SUI is the amount of water that we can get from the specific amount of snow. And we are selfish, actually, for this study. We would be focused on Switzerland, and Western Swiss Alps would be one of our case studies. And you can see the elevation map that I already showed, and some points that I will talk about them later to see the location of these points. The learning data set, the climate variables are coming from Aero5 land, 28 kilometers global and daily, which is reanalysis, and this brings the physics to our study. And the gridded data of SUI is coming from the SLF product, and it's the temperature index model product, and it's available from 1998 till 2022 with the resolution of 1 kilometer and daily. And for test data sets, we focus on later of 2014 and try to predict for current and also for future. And that's the reason that we use 2014, because till 2014, GCMs are historical, but after 2014, they are just projections. And the climate variables are coming from GCMs, as I mentioned. And the resolution is 28 kilometer, and we have used the downscale bias corrected NASA product for CMIP6. And here you can just see 3 names of the models. We do not need to go through the details of these models, but what I want to mention that why these 3 models is that we have done the study that for our features, how best one of the GCMs is matching to our region, because GCMs they are actually accurately predict climate, but probably for a wrong planet. And that's the reason that we do the bias correction, as well as some of these models are for a specific region perform better than the others. So we should focus on those. Here I'm just showing a video of some days. In the left, you can see the reference suite, which from green to blue, the suite is increasing and the dates are passing. And in the middle, you can see actually the estimated one, and the difference between them is also shown on the right. And the blue means actually overestimation, and red means underestimation. And you can see that it can vary from day to day. And we also give the quality band when we produce these data sets. And this quality bands coming from the distance matrix that are already introduced in the methodology. And with these quality bands, we can say that which day the product is more reliable. And here I'm showing the mean sweep through the region for 2014 till 2022 using the OSHD service, which is a black dash line, and it's our reference, and what we have estimated. And the average, you can see that, for example, in February and March, MIROC and MRI is doing better than Access ESM, but other months Access ESM is doing better than these 2 models, and shows that it's really vary between models, the output, and then we can have an ensemble of prediction for future. For accuracy assessment, as we are lucky from 2014 till 2022, we have already seen the reality of SWE, so we can do some cross-validation at least for these few years. And then we also do the validation against error 5, and also take a look at point-based analysis. And I will start with cross-validation. Here I'm showing on the right, you can see OSHD, which is our reference for March and May, average of that, and the Access ESM, which is our estimation based on this model. The suite, again, from green to blue, it increased. And in the left, I'm showing the difference between these 2 predictions based on different models, and you can see that it really varies. And if we are red, it means that we are underestimating, and blue means overestimation. In the average, you can see that it's going quite well. And in the validation against error 5 land, although the error 5 land actually, the resolution is really low resolution, but at least give us an opportunity to compare. And here we have the average of error 5 for March and for several years, for example, 2015, 16, and 17 for this presentation. And we compare this average to the average of OSHD service and the average of our estimation. And you can see that we are quite close to the OSHD, which is the reference when we are comparing with another data set like error 5. And again, red and blue shows the underestimation and overestimation. And point-based temporal analysis, that those 4 points that I showed in the elevation map, you can see that in blue, we have a OSHD service suite for 2015 till 2019. And for the red, you can see the estimated ones for these 4 points. And then instead of looking in average, we're looking just a point-based. And some years it's really good, and some years you can see that we have done this underestimation. And this is really important, actually, for our seminar. What is our perspective for future? Based on the methodology that we developed, we can see that in average, if I average OSHD for 2000 till 2022 for March, and compare it with our prediction for 2035 and 2060, for example, you can have that we have really less snow in future, and you can see that this less snow is high elevation is much more, and in 2060 is also much more. And this is the thing that we should think about it now. And in summary, if I want to give a summary, we introduced a hybrid downscaling method that actually overcome the temporal limitation of high resolution SWE by having a SWE for past, current, and future in 1 kilometer daily data sets. And it has a global use potential because we are using CMIP6 and ERA5. And in case that other countries have a high resolution SWE for some years, they can also predict or estimate for past or future. And because we are using GCMs, then we could have an ensemble of prediction. And the vision that we have used is to combine statistical and physics by using the ERA5, and also by having a temporal interval of climate variables, and using bias-corrected data set. We hope that we can have more accurate estimations. And by this, I will end the presentation, and thank you for your attention.
I will now introduce our second expert, Dr. Emmanuel Dubois. Emmanuel is a hydrogeologist with a passion for sustainable development. His research focuses on quantifying groundwater resources and exploring their potential to foster sustainable societal development. Having previously focused on characterizing the impact of global change on groundwater resources in Canada and Lebanon, he is currently engaged in developing a nature-based solution to mitigate flooding in Nouakchott, Mauritania. Thank you, Emmanuel, for joining us. The floor is yours, and hopefully you'll be able to pronounce this much better than I did.
Thank you. I'm going to also share my screen. Today, I'm mostly going to speak about the research I conducted on the impact of global change on groundwater recharge in cold and humid climates. So I used the example of southern Quebec in Canada as an example. So I conducted this research during my PhD at UQAM in Canada, which was part of a larger project funded by the Quebec Ministry of Environment, aiming at understanding or characterizing the expected impact of climate change on water resources to eventually implement mitigation measures. So first, we can start with a little introduction on groundwater recharge and define the process. So part of the precipitation that does not run off at the surface or is not directly evapotranspirated infiltrate into the soil and reach below the root zone. From there, it can flow laterally to the closest discharge area, or can be stored within the unsaturated zone, or can percolate through the unsaturated zone to eventually reach the saturated zone, and then participate to the replenishment of the aquifer. And that's why we call it groundwater recharge. So it's a key hydrological process because it contributes to the groundwater flow that sustain different uses, such as the river, or that will sustain the rivers, the wetlands, like various ecosystems, but also not represented on this scheme. The production of water for domestic water usage, or domestic water, industrial water, or agriculture. So beside the geological settings, groundwater recharge is also sensitive to surface processes, such as the climate, which will determine the temporal and spatial availability of liquid water, and the land cover, because it could favor or restrain infiltration and thus further impact the recharge. But then recharge is also partially responsible for the reactivity of aquifers to change in limit conditions, meaning the change, for example, at the surface. So this graph shows that the higher the groundwater recharge rate, so to the right, we're here in log scale. So the higher the groundwater recharge, the faster the groundwater response to changes in limit conditions, so to the bottom. So that to say that in humid conditions, so here highlighted in blue, the hydrogeological dynamic of these humid climates would be the fastest to be impacted by changes in climate condition in land cover. So overall, groundwater recharge is a key parameter for long-term water resource planning, especially in regions where water resources, surface water and groundwater are closely connected, or where groundwater is the main water supply. So when we think about how recharge is sensible to surface conditions, we have to think about global change, right? So we all know about like the expected certain rise in temperature that will also be more important in the northern latitude. So the relative changes in temperature or rise in temperature will be more important in the northern latitude, which is also the cold climate region. And also associated with these certain changes in temperature, we have very uncertain changes in precipitation. So also as climate change unfolds, some land cover might become more suitable or less suitable, especially in the cold climate area, because warmer temperature will extend the growing season at the expense of the winter season, which will make it more suitable, for example, for agriculture. And that will also impose biodiversity shifts throughout the year, while also reducing the snow cover. So all of this will impact the hydrological dynamics, which include also the groundwater recharge. So also if these changes can be relatively clear at the local scale, and the impact also can be clear at the local scale, it's relatively tricky to capture it at a larger scale. So considering the globally changing conditions and the potential impact on water resource in cold and humid climate, the goal of my research was to determine the driving processes of long-term and large-scale recharge in these climates. So we can start by a little overview of the data and methods I used throughout of my research. So first I used the case study of southern Quebec in Canada, which is roughly a little bit smaller than Switzerland, but in the same range of area. So it is composed of 8 river watersheds, all tributaries of the St. Lawrence River, and we named them from west to east, watershed 1 to watershed 8. So the climate there is a cold climate with hot summers, but without dry season, and that represent approximately 1,100 mm of precipitation per year, with an average, which includes 250 centimeters of snow during the winter period, and an average annual temperature of 5 degrees Celsius. So this area is mostly forested, but is also a strategic region for agriculture for the province of Quebec. Then just an overview of the workflow I used. So we used historical climate data on the 1961-2017 period, as well as a set of 12 climate scenarios with RCP 4.5, with a mix of RCP 4.5 and RCP 8.5. We then used constant land cover classification representing an average situation in 2015, and also land cover scenarios associated with RCP 4.5 and RCP 8.5. Then we used the hydro budget model to simulate transient spatially distributed groundwater recharge, and we calibrated the model at the regional scale. all of that allowed us to obtain a simulation of historical recharge over the past period, then a first set of 12 recharge scenarios considering a constant land cover, and then a second set of 12 recharge scenarios, but this time considering a transient land cover. So before looking at what will happen in the future, we wanted to understand a bit more what was the current and the past dynamic in recharge. So we calibrated the hydro budget model using river flow and base flow using recursive filters on the river flow, and we obtained very satisfactory results. I was actually really happy when I obtained this result during my PhD. I was relieved because it's an example on one gauging station. In red we have the simulated recharge, and in black we have the base flow, which is the target data for the calibration. And so we capture well the inter and intra-annual dynamics. And then we also wanted to check the parameter sensitivity of the model. So which were the most important or the most sensitive parameters in the simulation process. We realized that for the simulation of river flow, the parameters linked to the simulation of the snowpack, so in gray in this chart, were the most sensitive, while for the simulation of the recharge, it was the parameter linked to the simulation of the runoff in yellow, and then the parameters linked to the simulation of the soil frost that were the most sensitive. So once we were happy with the simulation results, we looked at the evolution of recharge throughout the year in the past period still. And we divided the simulation period in 3 19-year-long periods to check if there were any significant changes in between the last two periods in comparison to the first period. And so the orange backgrounds represent a significant increase between the considered period and the first period for a watershed. So we realized that we had significant increases in precipitation and temperature over the years. And surprisingly, these changes did not transmit onto the recharge. And we were surprised to not observe a decrease in recharge, which meant that either the increase in precipitation was not enough to impact the recharge, or that the increase in precipitation, that the increase in temperature was not enough to impact the recharge, or that the increase in precipitation balanced the increase in temperature, and that did not affect the recharge. So once we knew a bit more about the dynamic of the system, we looked into the impact of climate change on recharge. And to do so, we compared on monthly recharge rate. We compared the last two future periods, so represented with the yellow and the red box plot, to the reference, so to the 1981-2010 reference period, the gray box plot. And then on this graph, the blue background represent a significant increase in recharge between the future period and the reference period, and the orange background represent a significant decrease between the future period and the reference period. So we can see a pattern emerging here where the increase between the simulated increase in recharge between the cold month, so from December to March, where temperature is currently below 0 degrees Celsius, would balance the decrease during the rest of the year. And that was very important, because based on that, we checked how the changes in future climate would affect the changes in recharge. And we were able to identify thresholds in changes in future conditions linked to the significant changes in recharge. So just to explain a bit this dense graph, on the x-axis, for example, here we have the changes in precipitation, and on the y-axis we have the changes in recharge. So these changes, they are the changes between future period and reference period, and the colored boxes represent the significant changes. So we can see that all the significant increases in recharge were systematically associated with an increase in precipitation higher than 150 millimeter. And on the opposite, the significant decreases in recharge were systematically associated with an increase in precipitation lower than this threshold. We could do the same exercise with the temperature. And finally, we associated the significant increase in recharge with an increase of recharge during the cold month period higher than 25 millimeter, meaning that if we had an increase of recharge between December to March higher than 25 millimeter, then we were to expect an increase in recharge all year long. Yeah. But then all this was done with the hypothesis that land cover wouldn't change over time. So to correct that, well, we wanted to check what was the impact of land cover on the simulation in the future. So we produced this second set of recharge scenarios simulated with transient land cover. And this time we compared it to the first set of recharge scenario simulated with constant land cover by looking at the footprint of the significant changes in recharge. So for example, in orange, the orange envelope here represent the significant changes in recharge simulated with transient land cover and the RCP 4.5 scenario chain. While the orange, while the pink envelope represent the significant changes in recharge obtained with a constant land cover. And then for the RCP 8.5, the two set of recharge scenario mostly overlap. So what we observed is that with transient land cover, we simulated significant changes in recharge with a wider range of changes in temperature and in precipitation. As well, we tended to have higher recharge rate with the transient land cover with the RCP 4.5 scenario, which was associated with a massive afforestation in the study area. And to identify the process which was responsible for these changes, we had to look into the difference in runoff, like the difference in recharge between the two sets of scenario as a function of the difference in runoff between these two sets of scenario. And we realized that the significant differences between the two set of recharge scenario were associated with a decrease in runoff during the period from December to May. And this decrease in runoff was mostly associated with more intense land cover. So as a conclusion, as a outlook, I would say that we characterized the seasonality and the importance of the cold month for the hydrological dynamic in the region. Then we showed that the direction of changes in future recharge, so either increase or decrease, depended on if the increase during the cold month period would offset the decrease during the rest of the year. And that was very interesting because then we were able to identify these thresholds that would leading to the changes in future recharge. And I would say that these thresholds, the identification of this threshold is a very interesting way of communicating about the result, about studies on the impact of climate change. Then we also showed that land cover change increased the sensitivity of recharge to changing climatic conditions. And here again, the cold month period was key to understand the responsible processes. So thank you for your attention.